The number 13.8 billion years is the most sacred figure in astronomy, representing the hard limit where time itself theoretically began. But that number might be a hallucination, because we just found something in the deep dark that mathematically proves our timeline is a lie. The James Webb Space Telescope opened its golden eye and stared into the abyss, expecting to see infant stars born from the primordial fog. Instead, it saw monsters, massive, fully formed galaxies, sitting comfortably in a time period where the universe should have been empty gas and silence. This is the equivalent of finding a modern skyscraper buried in a dinosaur fossil. It defies every single law of cosmic evolution we possess. The atoms in your body were forged in stars, but if our timeline is wrong, we don't actually know the true origin of the matter that makes you. Astronomers are calling them universe breakers, because their very existence suggests the Big Bang might not have happened when or how we think it did. One specific candidate, a galaxy identified in the deep field, contains stars that appear to be older than the universe itself, a logical paradox. If the universe is only 13.8 billion years old, how can a galaxy exist that seemingly required 20 billion years to evolve into this shape? We are staring at a cosmic crime scene where the victim apparently died before the murderer was even born, and the physics do not make sense. The standard model of cosmology, the bedrock of all modern science, is currently screaming in agony because of these impossible photographs. At first, the scientists thought it was a mistake, a calibration error in the instruments, or a trick of the redshifted light bending through gravity. But the data held firm, confirming that these massive structures existed merely 500 million years after the theoretical beginning of time. You cannot build a galaxy with 100 billion stars in that short amount of time. There simply isn't enough gravity to pull the matter together. That era was supposed to be the Dark Ages, a time of chaotic hydrogen fog, not a time of structured spiraling order and heavy elements. This implies that the universe was already mature when we thought it was being born, pushing the start date back into the shadows of the unknown. Look up at the night sky from your backyard. The light hitting your retina is telling a story that might be a complete fabrication of our models. Some scientists are whispering about new physics, while others wonder if our understanding of light itself has been flawed for over a century. Physicist Mike Boylan-Colchin sounded the alarm, stating that if these masses are correct, we have fundamentally broken cosmology and need a new theory. We are not just rewriting a textbook. We are realizing that the universe is far stranger and potentially far older than we ever dared to dream. To understand the horror of this discovery, you have to understand how empty the early universe was supposed to be according to our simulations. Gravity takes eons to pull gas together, to ignite fusion, and to organize chaos into the spiral arms we see in the modern sky. These galaxies grew up too fast, like finding a fully grown oak tree 5 minutes after planting an acorn in the ground. In the Webb images, they look like faint red smudges, but those smudges represent mass concentrations that defy the baryon budget of the cosmos. If we can't explain how these galaxies exist, then our calculations for dark energy and dark matter might also be catastrophic failures. We are looking at something that logically cannot be there, creating a cognitive dissonance that is shaking the foundations of astronomy to its core. We built the most advanced time machine in human history, and it took us to a past that doesn't match the blueprints we wrote. It is the impossible early galaxy problem, a dull name for a crisis that threatens to dismantle the Big Bang theory entirely. Every star you see is part of a lineage, but if the lineage is broken, we don't know where the first ancestor actually came from. Are we misinterpreting the redshift? Is the universe static? These forbidden questions are suddenly back on the table for the first time in decades. One new paper suggests the universe might actually be 26.7 billion years old, doubling the timeline just to accommodate these ancient monsters. Imagine the vertigo of realizing that half of history was hidden from us, a vast epoch of time lost in the dark before we existed. We are observing the universe's baby pictures, only to find a fully grown adult staring back at the camera with ancient, tired eyes. The scientific community is quiet, not because there is nothing to say, but because the implications are too loud to ignore without panic. Galaxy ZFUDS 7329 is the smoking gun, a quiescent galaxy that stopped forming stars when the universe was barely awake. To be dead and quiescent so early means it lived a full, violent life before the universe had even finished its morning coffee. It contains more mass than the Milky Way, yet it condensed in a blink of an eye relative to cosmic timescales. Nature does not rush. Gravity is a slow sculptor. Yet here we see a masterpiece created in an impossible instant of creation. Unless dark matter behaves in ways we have never seen, this galaxy is a violation of the laws of structure formation. A rift has opened between observation and theory, and investigative journalists of the cosmos are scrambling to bridge the gap before the model collapses. It makes you feel insignificant, knowing that even our best measurements of reality are subject to such massive, glaring, and terrifying errors. We must now act as detectives at a crime scene where the laws of physics are the prime suspects in a cosmic cover-up. Is it modified gravity, primordial black holes, or is the expansion of the universe itself a misunderstanding of the light data we receive? The screen you are watching this on operates on quantum physics, but the macro physics of the sky are failing us right now. There is a subtle terror in realizing that the sky is not a clockwork mechanism, but a chaotic puzzle we haven't actually solved. To understand why this is happening, we have to go back to what we thought was the beginning of everything we know. The story of the Big Bang was clean, elegant, and simple, but the universe is refusing to cooperate with our desire for elegance. The images coming from deep space are beautiful, but to a cosmologist, they look like a horrifying mathematical disaster. We are about to dive into the evidence that suggests our universe is not just older, but fundamentally different than we believed. Prepare yourself, because the deeper we look, the darker the mystery becomes, and the answers are not comforting to the human mind. To understand why astronomers are currently sweating in their observatories, we first need to look at the Standard Model of Cosmology, also known as Lambda CDM. For decades, this has been the detective's handbook, the set of rules that explains everything from the microwave background radiation to the distribution of galaxy clusters. It assumes that the universe began in a hot, dense state and has been expanding ever since, governed by the invisible hand of cold, dark matter, the CDM in the name. According to this model, the early universe was a smooth, featureless sea of particles. It was chaotic but uniform. There were no structures, no lights, and certainly no monsters. Gravity, being the weakest force in the universe, had to work overtime, slowly pulling tiny fluctuations of density together over hundreds of millions of years to form the very first halos of dark matter. This process is slow. It is agonizingly slow. It is a cosmic construction project that requires an immense budget of time, a budget that the Standard Model has calculated down to the decimal point. And this is where the crime scene begins to show evidence of tampering, because the timeline we see in the telescope does not match the timeline in the handbook. Let's talk about the Dark Ages. In the accepted timeline, after the Big Bang, the universe went dark for a long time. The hydrogen gas was neutral, absorbing light, creating a fog that hid everything. The first stars, population 3 stars, weren't supposed to turn on until about 100 to 200 million years into the timeline. And galaxies? Real, structured galaxies? They are supposed to be built bottom-up. You start with small clumps, like cosmic Lego bricks, and over billions of years, they merge to form the massive spirals and ellipticals we see today. A galaxy with the mass of our Milky Way shouldn't exist in the infancy of the cosmos, because there hasn't been enough time for the merger trees, the family history of galaxy collisions, to grow that large. It's like walking into a kindergarten and finding a fully grown, battle-hardened soldier sitting in the corner. The biology doesn't allow it. The physics shouldn't allow it. Yet, when the James Webb Space Telescope pointed its hexagonal mirrors at a patch of sky near the Big Dipper, it found exactly that. Fully grown soldiers in the cosmic nursery. The specific suspects in this investigation are 6 massive galaxies identified by a team led by astrophysicist Ivo Labbé from Swinburne University of Technology. These aren't just vague anomalies. They are statistical impossibilities under the current paradigm. The data suggests these galaxies existed between 500 million and 700 million years after the Big Bang. In human terms, if the universe is a 100-year-old man, these galaxies were fully formed when he was a 3-day-old infant. But the terrifying part isn't just their age, it's their weight. These galaxies are estimated to contain as much mass in stars as our modern Milky Way. Do the math. The Milky Way took 13 billion years to accumulate its bulk, cannibalizing dwarf galaxies and sipping gas slowly from the intergalactic medium. These new discoveries managed to do the same amount of work in less than 5% of the time. To achieve this, they would have needed to convert gas into stars at 100% efficiency, leaving nothing behind, which is physically impossible because star formation is a messy, inefficient process that blasts gas away rather than consuming it all. The term scientists use for this efficiency problem is the baryon conversion ratio. In the local universe, the reality we inhabit and understand, galaxies are terrible at making stars. They are wasteful. For every cloud of gas that collapses into a star, massive amounts of material are blown out by supernova winds or heated up by black holes until it can't collapse. Typically, a galaxy converts only about 10% to 20% of its available gas into stars. This is the speed limit of cosmic manufacturing. But for Lebbe's galaxies to exist this early, they would have needed to break this limit, converting nearly every single atom of available hydrogen into a star instantly. It implies a violence and a speed of creation that we have never witnessed. It suggests that in the early universe, the laws of thermodynamics and gravity were behaving in a way that looks unnatural to us. If they weren't breaking the efficiency limit, then they must have had access to vast reservoirs of matter that our simulations say shouldn't be there. Either way, the blueprint is wrong. Let's dig deeper into the redshift. This is the ruler we use to measure the universe. As space expands, light waves stretch out, shifting towards the red end of the spectrum. The higher the z-score or redshift, the older and more distant the object. The galaxies in question have redshifts around z=9 or z=10. When the data first came down from the telescope, the investigative team didn't believe it. It was too perfect, too bright. They spent months trying to find the error. Was it a calibration issue? Was the telescope's mirror slightly misaligned? Was it a low redshift interloper, a dusty, nearby galaxy masquerading as an ancient one? In astronomy, dust can make a young galaxy look red and old, acting like a disguise. They stripped the data apart, layer by layer, looking for the mask. But the mask wasn't there. The spectroscopy confirmed that these weren't imposters. They were ancient, they were massive, and they were real. The realization hit the team like a cold wave. The universe was teeming with giants when it should have been empty. The implications of the universe breakers go beyond just galaxy formation. They threaten our understanding of dark matter itself. Dark matter is the scaffolding of the universe. It forms the invisible halos that pull normal matter in. In the lambda CDM model, these halos grow over time. You can't have a massive galaxy without a massive dark matter halo to anchor it. If these galaxies are real, it means the dark matter halos grew exponentially faster than our computer simulations predict. This forces us to ask a chilling question. What if dark matter isn't what we think it is? What if it's not cold and collisionless? Maybe in the early universe, dark matter had properties that catalyzed this hypergrowth. Or, perhaps even more frightening, maybe we don't understand gravity at cosmic scales. Some theorists are dusting off modified Newtonian dynamics theories, suggesting that maybe dark matter doesn't exist at all, and our equations for gravity are just wrong. If gravity is stronger than we think in the early universe, it would explain the rapid collapse, but it would also break every other model we have for the modern universe. There is another suspect in this lineup, one that is perhaps even more terrifying than a broken model: primordial black holes. Some physicists have suggested that the seeds for these massive galaxies weren't dark matter halos, but supermassive black holes that formed directly from the collapse of the Big Bang itself. In standard physics, black holes form from dead stars. But direct collapse black holes are theoretical monsters that skip the star phase entirely. If the early universe was speckled with these heavy anchors, they could have pulled gas in at a ferocious rate, accreting matter faster than the Eddington limit allows. This would create bright, massive objects that look like galaxies, but are powered by singular points of infinite density. If this is true, then the early universe was a minefield of event horizons, a dark and violent epoch dominated not by starlight, but by the crushing gravity of singularities. It changes our origin story from a slow dawn of light to a sudden, violent eruption of gravity traps. We must also consider the possibility that our fundamental ruler, the expansion rate of the universe, is broken. This is known as the Hubble tension. We measure the expansion rate using two methods: the cosmic microwave background, the echo of the Big Bang, and supernovae, standard candles in the local universe. The problem is, these two methods give different answers. They do not agree. The universe seems to be expanding at different speeds depending on how you look at it. The discovery of these impossible galaxies adds fuel to this fire. If the universe is expanding differently than we thought, or if the expansion history is more complex, it might shift the age of the universe entirely. As mentioned, some radical theories now push the age to 26 billion years to fit these galaxies in. Imagine the existential vertigo of realizing we are living in a universe twice as old as we thought. It means half of cosmic history is a ghost story, a period of time that we have completely missed, filled with civilizations and stars that lived and died before we even started our clock. Let's look closely at one specific object, CEERS 93316. When it was first spotted, the photometric data suggested a redshift of 16.7. If that had held up, it would have placed the galaxy just 250 million years after the Big Bang. A monster at z equals 16.7 would have shattered physics instantly. Later spectroscopy revised this down, revealing it was likely a closer galaxy with strong emission lines that confused the sensors. This brought a momentary sigh of relief. See, it's just an error. But that relief was short-lived. While some candidates turned out to be imposters, others like ZFUDS 7329 stood their ground. The ones that remained confirmed the trend. We cannot dismiss the anomaly just because a few suspects were exonerated. The remaining evidence is robust, and it points to a systematic failure in our understanding. We are like detectives who found one fake fingerprint but ignored the dead body lying in plain sight. The body is real. The massive galaxies at z equals 10 are real, and they are screaming at us. What does it feel like to be an astronomer right now? It feels like vertigo. Dr. Erica Nelson from the University of Colorado Boulder, who was part of the team analyzing the data, described looking at the images and feeling that it just shouldn't be there. There is an emotional weight to this data. It's not just numbers. It's a violation of the order of things. We find comfort in the slow, predictable evolution of the cosmos. It implies safety. It implies that we can predict the future because we understand the past. But if the past was a wild, hyper-efficient, impossible era of monster galaxies, then the universe is more volatile than we admit. It suggests that fine-tuning, the idea that the universe is perfectly set up for life, might be a fragile illusion. If the parameters of star formation were different back then, why did they change? What turned off the hyper-efficiency? Or are we missing a hidden force, a fifth force of nature that only acted in the high-density environment of the early cosmos? Let's re-examine the baryon budget with the scrutiny of a forensic accountant. The universe has a fixed amount of normal matter, baryons, protons, neutrons, the stuff you and I are made of. The rest is dark matter and dark energy. In the standard model, only a specific fraction of baryons should fall into galaxies. The rest should be floating in the intergalactic medium, the space between spaces. These new galaxies are baryon hoarders. They seem to have captured almost all the available baryons in their vicinity. This is suspicious. It's like finding a small town where every single resident is a billionaire. It's statistically unlikely unless the system is rigged. Who or what rigged the early universe to shove so much matter into these small pockets of space so quickly? Is it possible that the cosmic web, the filaments of matter that connect the universe, was much thicker and denser in the past? If so, our maps of the early universe are too empty. We are drawing a desert when we should be drawing a jungle. This leads us to the top-down versus bottom-up theory debate, a cold case that was supposed to be solved decades ago. The lambda CDM model is strictly bottom-up. Small things merge to make big things. But in the 1970s and 80s, there was a competing theory called top-down formation, where massive sheets of matter collapsed purely under gravity to form giant pancakes that then fragmented into galaxies. We discarded this theory because the evidence didn't fit. But these massive, early galaxies look suspiciously like they formed top-down. They appeared suddenly, fully formed and massive. Are we seeing the ghosts of a dead theory coming back to haunt us? If the universe forms structures top-down, then the early universe was a place of titanic collapses, where entire clusters of galaxies formed in single, catastrophic events. It changes the narrative from a slow construction to a series of violent, sudden births. It makes the early universe a much more dangerous and dynamic place. We must also talk about the light itself. We assume that the light we see from these galaxies is coming from stars. But what if we are wrong about the source? What if these objects are dark stars? This is a theoretical type of star powered not by nuclear fusion, but by the annihilation of dark matter particles. These stars would be millions of times more massive than our Sun, puffed up by the heat of dark matter dying in their cores. They would be cool, red, and incredibly bright. Exactly what the James Webb telescope is seeing. If these universe breakers are actually supermassive dark stars, it saves the timeline but introduces a new horror. That the early universe was populated by single stars the size of galaxies, burning on invisible fuel. It would mean that dark matter isn't just a gravitational ghost, but a fuel source that powered the first epoch of light. It transforms the universe from a nuclear reactor into a dark matter engine. But if they aren't dark stars and they aren't numerical errors, we are left with the cosmic variance defense. This is the idea that maybe we just got lucky or unlucky. Maybe the James Webb telescope just happened to point at a freakishly dense patch of the universe. It's like scooping a cup of water from the ocean and catching a rare fish. It doesn't mean the whole ocean is full of them. However, the statistical probability of hitting such a dense patch in the small field of view of the telescope is vanishingly small. We have looked in different directions now, and the monsters keep appearing. They are not rare beasts, they are the herd. The cosmic variance excuse is running thin. The homogeneity of the universe, the idea that it looks the same everywhere, is being challenged. If the universe is clumpier than we thought, then the smooth expansion of the Big Bang might have been more like an explosion of shrapnel, uneven and chaotic. There is a disturbing parallel here to the ultraviolet catastrophe of the early 20th century, where classical physics predicted infinite energy and quantum mechanics was born to solve it. We are facing a mass catastrophe. Our classical cosmological physics predicts zero mass at this redshift, and we are finding infinity relative to the prediction. This usually signals that a paradigm shift is imminent. We are at the edge of a cliff in our knowledge. The scientists writing these papers are using cautious language, tension, anomaly, challenge. But the subtext is panic. They are realizing that the lambda CDM model might be an approximation that works for the middle-aged universe, but fails completely for the birth and death of the cosmos. We are living in a model that is fraying at the edges, and when the edges fray, the monsters get in. The universe is not behaving as we mandated, it is behaving wild. Let's consider the initial conditions. When we run simulations of the universe, we have to input the starting settings, the density, the temperature, the fluctuation amplitude. We get these numbers from the cosmic microwave background. But what if the map is wrong? What if the fluctuations in the early universe were non-Gaussian? In simple terms, this means the dice were loaded. If the early universe had more extreme density spikes than a bell curve allows, it would explain these galaxies. But it would also mean that the mechanism of the Big Bang itself, inflation, was different. Inflation is the theory that the universe expanded faster than light for a fraction of a second. If non-Gaussianities exist, it implies that inflation was rough, turbulent, and violent, distinct from the smooth, slow-roll inflation we teach in universities. It suggests a chaotic birth that imprinted deep, heavy scars on the fabric of space-time, scars that became these impossible galaxies. The mystery deepens when we look at the chemistry. These high redshift galaxies should be, quote, chemically primitive. They should be made almost entirely of hydrogen and helium. Heavy elements, carbon, oxygen, iron, are made in stars and require generations of stellar life and death to accumulate. Yet preliminary spectral data hints that some of these galaxies are surprisingly enriched with heavy elements. This is the metallicity problem. How can a toddler have the wrinkles and scars of an old man? If there is abundant oxygen and carbon in these galaxies just 500 million years after the start, it means thousands of generations of stars lived and died in a frenzied burst of activity that is practically instantaneous on cosmic scales. It implies a rate of evolution that borders on the unnatural. It's as if time itself was moving faster in the early universe, compressing billions of years of evolution into mere millions. We must revisit the concept of time. We assume time flows at a constant rate, governed by general relativity. But looking at these galaxies, one wonders if our perception of cosmic time is linear. Is it possible that in the high-density epochs of the early universe, the clock of structure formation ticked differently? While this sounds like science fiction, in the realm of high-gravity environments, time dilation is real. However, usually, gravity slows time down. For these galaxies to evolve faster, they would need the opposite. It's a paradox. The physical evidence demands a history that is longer than the timeline allows. This is why the old universe theory, 26.7 billion years, is gaining traction in the fringes. It is the only theory that gives these galaxies enough room to breathe. But accepting it means throwing away the Big Bang date, the one fact every schoolchild knows. It means admitting we were wrong about the birthday of existence. Let's focus on the little red dots. This is the nickname astronomers have given to a specific class of these objects found in the Webb data. They are compact, extremely red, and baffling. Their redness comes from the fact that their UV light has been stretched by the expansion of space into the infrared. But their compactness is the key. They are tiny, sometimes only a few hundred light-years across, but they pack the mass of billions of suns. They are incredibly dense balls of stars. In our local universe, star clusters this dense are rare and usually unstable. For entire galaxies to exist in this hyperdense state suggests that the early universe was a pressure cooker. The majestic spiral arms we love, like our Andromeda or Milky Way, are relaxed structures. These little red dots are tense, compressed, and tightly wound. They look like coiled springs waiting to explode. They represent a mode of galaxy existence that is alien to our quiet corner of space. The investigative trail leads us back to the dust. We mentioned dust as a disguise, but dust itself is a mystery at this epoch. Dust is complex molecules, soot, silicates. It is made by old, dying stars. Finding large amounts of dust in the early universe is like finding ashes in a fireplace that was just built. You need fire to make ash. If these galaxies are dusty, which some data suggests, it doubles down on the impossible age problem. It confirms that a massive cycle of stellar death happened before we thought the first stars were even born. Where did this dust come from? Some hypothesize supernovae factories, huge populations of massive stars that lived fast and died young, polluting the cosmos with dust instantly. But this requires a top-heavy initial mass function, meaning the early universe preferred making monster stars rather than small ones like our Sun. If true, the early universe was a blindingly bright, short-lived fireworks display of giants. What if we are looking at the great attractor of the early universe? We know that in the modern universe, galaxies are flowing towards gravitationally dense points. In the early universe, these massive galaxies might have acted as nodes in the cosmic web, anchoring the flow of gas. They are the spiders in the web. Their existence suggests that the web was spun much earlier than we thought. Simulation projects like Millennium or Illustris show the web growing slowly. These real-world observations suggest the web snapped into place violently. The contrast between the void and the filament was sharper. This means the early universe was a place of extreme contrast, absolute nothingness versus extreme density. It wasn't a smooth soup, it was a jagged landscape of peaks and valleys, and we are currently living in the calm, eroded aftermath of that jagged beginning. We missed the mountain building phase, we are just hiking on the hills. There is a psychological horror in the isolated nature of these finds. If you were an observer inside one of these early massive galaxies, looking out, you would see nothing. The universe around you would be largely neutral hydrogen fog. You would be on an island of light in an ocean of absolute dark. Because the other galaxies haven't formed yet or are too dim, you would feel like the only object in existence. It is a lonely, solipsistic existence. These galaxies are cosmic orphans, born before their siblings. The fact that they exist implies that the universe is capable of creating isolated pockets of high order amidst chaos. It challenges the Copernican principle that says there is nothing special about our location or time. Maybe there is something special about specific locations in the early cosmos that allowed these anomalies to grow. Maybe the laws of physics aren't as uniform as we pray they are. Let's talk about the sound. In the early universe, sound waves called baryonic acoustic oscillations, BAO, rippled through the plasma. These pressure waves helped pile up matter. If these galaxies are real, the sound of the Big Bang might have been louder or different frequencies than we calculated. These galaxies might be the frozen echoes of a much louder creation event. The density waves that created them had to have higher amplitude. We are essentially analyzing the recording of the Big Bang and finding notes that shouldn't be there. A heavy bass note where there should be silence. This implies that the bang itself had a texture or a structure that our smooth inflation models ignore. We are hearing the fingerprints of the mechanism that triggered existence, and it sounds violent, structured, and deliberate. The feedback loop problem is another piece of evidence that doesn't fit. In modern galaxies, when stars form, they push gas away, feedback. This regulates growth. It stops the galaxy from consuming itself. For these early galaxies to get so big, so fast, the feedback mechanisms must have failed. The gas didn't get pushed away. It kept falling in. Why? Was the gravity so intense it crushed the stellar winds? Or was the gas falling in so fast, cold accretion streams, that the stars couldn't push back? If feedback failed, it means the self-regulating thermostat of galaxy formation was broken in the early universe. It allowed for runaway growth, a cancer-like growth of structure. This runaway growth is what created these monsters. It suggests a period of unchecked cosmic consumption before the universe learned to regulate itself. We are also forced to reconsider the reionization epoch. This is the period when the first stars turned on and burned away the hydrogen fog, making the universe transparent. We thought this happened gradually, ending around 1 billion years after the Big Bang. But if these massive galaxies were there at 500 million years, they would have been blasting out UV radiation like searchlights. They would have reionized the universe much faster and earlier in patches. They would have punched bubbles of transparency in the dark ages. We might be looking at a Swiss cheese universe where massive bubbles of clear space surrounded these giants while the rest was still dark. It complicates the timeline of when the lights turned on. It wasn't a dawn, it was a series of flashlights flicking on in a dark room, chaotic and uncoordinated. The black swan logic applies here. We only needed to find one galaxy older than the universe to break the model. We found 6. Now we are finding dozens. This is no longer a swan. It's a migration. The sheer number of these objects is the most damning evidence against the standard model. If it was just one, we could plead anomaly. But a population means a process. There is a systematic mechanism at play that we have missed. It's like discovering a hidden room in your house that has been there for 50 years. Filled with machinery you don't understand, humming with power. We have lived in this universe our whole lives, thinking we knew the floor plan. Now we realize we have only been living in the foyer, and the real machinery is hidden in the walls of the deep past. Consider the energy density. To build a galaxy of $10 carat, $11 solar masses in 500 million years requires an energy infall rate that is staggering. The gravitational potential energy released by this collapse would heat the gas to millions of degrees. How did it cool down fast enough to form stars? Hot gas doesn't make stars. Only cold, dense gas does. This is the cooling problem. The gas should have been too hot to collapse. Something chilled it. Did the heavy elements, the mysterious dust, act as a supercoolant? Or did the dark matter halo have a different profile that allowed for rapid cooling? We are looking at a thermodynamic miracle. The universe managed to refrigerate a burning inferno instantly to create these stellar nurseries. It defies the thermal history we have written. The skepticism is healthy. We must remain skeptical. But the detective in us has to look at the track record. Every time we build a bigger telescope, we find that the universe is more complex than we thought. Hubble showed us the deep field. Webb is showing us the impossible field. The trend is clear. We underestimate the cosmos. We always bet on simplicity, and we always lose. The universe is inherently maximalist. It builds big, it builds early, and it builds fast. Our models are conservative, designed by human minds that like linear progression. The universe doesn't care about our linear progression. It appears to have burst into existence with a complexity that was ready-made. This concept of a ready-made universe is unsettling because it borders on the arguments for intelligent design, though in a scientific context, it simply suggests initial conditions were far more tuned for complexity than randomness suggests. Let's talk about the Crisis in Cosmology conference. Yes, that's a real thing. Scientists are gathering to yell at each other about these slides. The tension in the room is palpable. You have the experimentalists holding the Webb data like a weapon, and the theorists holding their lambda CDM equations like a shield. The experimentalists are saying, look at this photo. The theorists are saying, your photo is impossible. This standoff cannot last. One side has to break. History tells us that observation always wins eventually. If the map doesn't match the territory, you burn the map. We are currently smelling the smoke of the burning map. The Standard Model has survived for decades, explaining the CMB, the large-scale structure, the expansion. But it is choking on these galaxies. It might not die today, but it is definitely bleeding. What is the alternative? If we burn the map, what do we replace it with? Early dark energy is a strong contender. This theory suggests that dark energy, the force pushing the universe apart, was active in the early universe, then turned off, then turned back on again later. A pulse of anti-gravity that messed with the expansion rate. If early dark energy existed, it would change the ruler we use to measure time, potentially fixing the age gap. But it feels like a cheat code. It feels like adding a new variable just to make the math work. It's messy. Nature is usually elegant, but maybe nature is messy. Maybe the vacuum energy of space is dynamic, shifting and changing phase like water freezing to ice. If the vacuum itself is unstable, then the ground we stand on is not constant. Another alternative is fuzzy dark matter. Instead of being heavy particles, maybe dark matter is a wave, an ultralight boson that behaves like a quantum fluid on galactic scales. This wave-like nature would create interference patterns, clumping matter together differently than particles would. It allows for earlier structure formation. It turns the universe into a giant quantum superfluid experiment. If this is true, the galaxies we see are the crests of giant quantum waves. We are living inside a wave function. It connects the smallest scale, quantum mechanics, with the largest scale, galaxies, in a way that unifies physics. It's a beautiful solution, but it means our current view of particles is woefully inadequate. We are swimming in a sea of waves we cannot see. Let's look at the sheer visual weirdness of these galaxies again. They are not just big, they are compact. They are incredibly dense. Imagine the night sky on a planet inside one of these galaxies. The stars would be so packed together that the sky wouldn't be black with points of light. It would be a blazing sheet of white. Night would not exist. The radiation environment would be intense, likely sterilizing any planets that tried to form. These are not habitable zones. They are nuclear furnaces. The fact that so much matter was crammed into such small volumes tells us that gravity was acting like a trash compactor. It was crushing matter down. This high density might be the clue. Maybe the early universe didn't expand uniformly. Maybe it had knots where space didn't stretch, trapping matter in pockets. We are also seeing quenching. Quenching is when a galaxy dies. It stops forming stars. We found a quenched galaxy at z equals 4.6, but the progenitors, the parents of that galaxy, must have lived and died even earlier. To kill a galaxy, you need to run out of gas or heat it up so much it can't collapse. For a galaxy to be dead that early means it lived its entire life cycle, birth, peak, and death, in the time it takes our sun to orbit the galaxy twice. It's a live fast, die young scenario on a cosmic scale. It implies that the early universe was a place of rapid turnover, generations of galaxies rising and falling like breaths. We are looking at the graveyard of the first generation, and it is surprisingly full. The anthropic principle rears its head here. If the universe had formed structures any faster, the radiation would have been too intense for life. If it had formed them slower, the universe would be empty. We seem to exist in a Goldilocks universe. But these new findings suggest we are closer to the too fast edge than we thought. The universe skirted the line of being too violent for life. We might be the survivors of a cosmic close call. If those early monsters had kept growing, they might have consumed everything, leaving nothing for the quiet, habitable suburbs like the Milky Way. We exist because the monsters stopped eating. Why did they stop? That is the next question. There is a technological horror here too. We built Webb to see the beginning. We wanted to see the first light. Instead, we found a curtain. These galaxies act like a curtain, blocking our view of what came before. Because they are already fully formed, the true beginning is pushed even further back, potentially beyond the reach of Webb. We might have built a $10 billion machine that is still not powerful enough to see the moment of creation, because the creation happened in the dark, hidden by the very monsters we are looking at. We are chasing a horizon that keeps moving away from us. The first light is elusive. It doesn't want to be seen. Let's summarize the crime scene so far. The victim, the standard model of cosmology. The cause of death, blunt force trauma by 6 massive galaxies. The time of death, approximately 500 million years after the Big Bang. The suspects, primordial black holes, early dark energy, modified gravity, or a misunderstanding of light itself. The detective, humanity, holding a golden telescope, looking confused. The investigation is ongoing, but the preliminary report is terrifying. It says that we do not know where we came from. The story we told ourselves, the slow, cold evolution, is a bedtime story. The reality was hot, fast, and crowded. What happens next? The spectroscopic confirmations are rolling in. We are moving from photometric candidates, guesses based on color, to confirmed redshifts. Every confirmation drives another nail into the coffin of the old model. We are seeing papers published with titles like Panic. Literally, that was a title. The scientific community is not immune to emotion. There is excitement, yes, but there is also the fear of obsolescence. A physicist who spent 40 years studying lambda CDM might be watching their life's work crumble, but that is science. It destroys to create. We are in the destruction phase. We must also consider the unknown unknowns. If we missed galaxies this big, what else are we missing? Are there objects that don't shine with starlight? Dark galaxies made entirely of dark matter? Or objects that emit radiation we aren't looking for? The universe is 95% dark matter plus energy. We are obsessing over the 5% that glows. These massive galaxies are the tip of an iceberg. If the tip is this big, the iceberg underneath the dark sector structure must be Titanic. We are sailing the Titanic into that iceberg, and we just spotted the white glimmer on the horizon. The lithium problem is an older mystery that might be connected. The Big Bang predicted a certain amount of lithium. We see way less. Now we see way more galaxies. Maybe the lithium was consumed or destroyed in these early monster galaxies. Maybe the anomalies are connected. A grand unified anomaly. If we solve the galaxy problem, maybe we solve the lithium problem and the Hubble tension all at once. It's a house of cards. If you pull the galaxy formation card, the whole house might fall down, or it might reassemble into something stronger. We are pulling the card right now. Let's return to the impossible. Science hates that word. Nothing is impossible, only improbable. But statistically, these galaxies are 5 sigma or 6 sigma events. In science, 5 sigma is the gold standard for discovery, like the Higgs boson. But here, the discovery is a contradiction. It's a 5 sigma proof that we are wrong. We are holding a smoking gun that proves the laws of physics were violated, or at least the laws as we wrote them. The universe didn't break the law, we wrote the wrong law. We are the legislators of reality. And the citizens, the galaxies, are revolting. Think about the voids. Between these massive galaxies lie vast cosmic voids. If the galaxies amassed matter this quickly, they must have stripped the voids bare. The contrast between something and nothing in the early universe was absolute. Today, there is wispy gas everywhere. Back then, it might have been binary. Either you were in a monster galaxy, or you were in the absolute vacuum. It was a binary universe. 1 or 0. Life or death. Light or dark. The gray areas hadn't evolved yet. The nuance of the universe came later. The beginning was stark. We are approaching the 100th scene of this investigation, and we haven't even touched on the quasars. Quasars are supermassive black holes eating gas. We see them at z=7. To grow a black hole that big, you need, you guessed it, more time than the universe allows. The impossible galaxies and the impossible quasars are best friends. They are co-conspirators. They both tell the same alibi. We grew up fast, but physics says you can't eat that fast. The black holes would choke. The radiation pressure would stop the food from falling in. Yet they exist. They are fat and happy in a universe that should be starving them. Could it be mergers? Maybe these galaxies aren't one big thing, but lots of small things smashing together. The resolution of Webb is good, but maybe not good enough to see the cracks. If they are mergers, it helps the timeline a little, but not enough. Mergers take time too. They are a dance. You can't just smash a billion stars together instantly without chaos. The images look too smooth, too regular to be active train wrecks. They look like settled discoidal galaxies. They look peaceful. That is the weirdest part. They are calm, impossible monsters. The stellar mass density global average is rising. When we integrate all these new galaxies, the total density of stars in the early universe goes up by a factor of 10 or 100 compared to models. This isn't a rounding error. This is a missing order of magnitude. It's like estimating the population of a city to be 10,000 and finding out it's 1 million. The census is broken. The universe is crowded. We thought it was a frontier town. It's a metropolis. Cosmic dawn is the poetic name for this era. But cosmic noon is when star formation peaked, around z=2. We thought the dawn was dim. Now the dawn looks as bright as the noon. This flattens the history of the universe. Instead of a curve that goes up and down, it's a plateau. Structure formed early and stayed high. It means the universe hit the ground running. It didn't stumble into existence, it sprinted. What gave it that initial kick? What was the energy source that drove this sprint? This brings us back to the multiverse theory, strictly as a speculative mechanism. In eternal inflation, many universes bubble up. Some have different laws. Maybe our bubble collided with another bubble early on? A bubble collision could inject energy and density, jump-starting galaxy formation. It sounds crazy, but when the standard model fails, the crazy theories get a seat at the table. Are these galaxies the bruises left by a collision with another universe? A cosmic fender bender that compressed our gas? Or is it a simulation artifact? This is the Matrix argument. If the universe is a simulation, maybe the programmers got lazy with the initial conditions. Maybe they just pasted in some galaxies to make the background look nice? It's a philosophical joke, but the fine-tuning of these galaxies is so precise it feels artificial. They are too perfect. Nature usually makes mistakes. These look like procedural generation gone wrong, spawning high-level enemies in the starting zone. We need to talk about population 3 stars again. We have never seen one. They are the Holy Grail, pure hydrogen stars. Massive, short-lived. These massive galaxies might have hidden them. Or maybe, population 3 stars never existed? Maybe the universe skipped that generation and went straight to dirty, metal-rich stars? If so, we need to rewrite stellar nucleosynthesis. The periodic table itself has a different history. The carbon in your DNA might have a different origin story. The investigative journalist in me looks at the funding. Webb cost $10 billion. It was worth every penny because it broke the universe. If we hadn't built it, we would still be sleeping, thinking the standard model was safe. Ignorance was bliss. Now we are awake, and we are confused. The data is public. Anyone can download it. You can look at the FITS files yourself. The anomaly is not hidden in a vault. It is on the internet. We are crowdsourcing the crisis. To verify these impossible monsters, we rely on one of the universe's most elegant tricks: gravitational lensing. This is nature's magnifying glass. When a massive cluster of galaxies sits between us and a distant background object, the gravity of the cluster warps the fabric of spacetime itself. The light from the distant object has to follow this curved path, bending around the cluster like water flowing around a rock in a stream. This bending magnifies the image, brightening it and stretching it into arcs. Without this natural telescope, we might never have seen some of these high redshift galaxies at all. But here's the twist. For lensing to work this effectively, the mass of the foreground cluster must be immense, and the alignment must be perfect. The fact that we are finding these ancient galaxies magnified by foreground clusters adds another layer of complexity to the mass distribution puzzle. We are using gravity to see back in time, and gravity is showing us things that gravity itself shouldn't have been able to build yet. It's a hall of mirrors where the reflections are revealing the cracks in the glass. Let's talk about the specific instrument responsible for this existential dread: the Near-Infrared Camera, or NIR-CAM. This is the golden eye of the James Webb Space Telescope. It was designed to catch the faint, stretched light of the first stars. Light that was emitted as ultraviolet rays billions of years ago has traveled through the expanding universe, stretching out into the infrared spectrum. Human eyes cannot see this light. To us, the early universe is pitch black. But to NIR-CAM, it is ablaze. The sensors on this machine are cooled to near absolute zero to prevent their own heat from blinding them. They are looking for the Lyman break, a specific drop-off in the spectrum of light that acts as a chemical fingerprint for hydrogen absorption. When astronomers see this break, they know they are looking at the edge of the visible universe. But finding the Lyman break at such high redshifts, in such bright objects, was like finding a fingerprint on a ceiling. It implies a giant was standing there. The confusion has resurrected a theory that was long considered dead and buried: tired light. Proposed by Fritz Zwicky in 1929, this theory suggested that the universe isn't expanding at all. Instead, Zwicky argued that photons, particles of light, simply lose energy as they travel vast distances, like a runner getting exhausted after a marathon. As they lose energy, their wavelength stretches, shifting to red. If tired light is true, the Big Bang never happened. The universe is static, eternal, and infinite. For decades, this theory was mocked because it couldn't explain the cosmic microwave background or the time dilation of supernovae. But with the new Webb data showing fully formed galaxies where they shouldn't be, some fringe theorists are whispering Zwicky's name again. If the universe is static, there is no beginning, and therefore no time limit on galaxy formation. These galaxies could be trillions of years old. It solves the impossible early galaxy problem by removing the concept of early entirely. However, the tired light theory carries its own cosmic horror. If the universe is static and eternal, it means we are trapped in a never-ending cycle with no beginning and no end. It eliminates the moment of creation, but standard cosmology fights back with the time dilation of supernovae. We see distant explosions happening in slow motion, which proves space is expanding. Tired light cannot explain why a distant supernova takes weeks to fade while a nearby one takes days. So we are likely not in a static universe. We are in an expanding one. This brings us back to the terrifying reality. The universe is expanding, the Big Bang did happen, but our timeline of what happened immediately after is catastrophically wrong. We are stuck between a dead theory, tired light, and a broken theory, lambda CDM. We are currently navigating the void without a compass, and the monsters are watching. Let's delve into the Balmer break. This is another spectral feature, different from the Lyman break, and it tells a story about age. The Balmer break appears in the spectrum of galaxies that contain older populations of stars that have been burning for hundreds of millions of years. To find a strong Balmer break in a galaxy at z=10 is devastating to the standard model. It means those stars started forming at z=20 or z=30, effectively at the very instant the Big Bang cooled down. It implies that star formation started immediately. There was no dark age. The lights turned on the moment the universe existed. It transforms the early universe from a slow awakening into a sudden, blinding flash of brilliance. It suggests that the conditions for life and chemistry were present almost instantly. The universe didn't wait. Why did we think it waited? Because our simulations were cautious. Nature is not cautious. This leads to the disturbing Fermi paradox implication. The Fermi paradox asks, where is everybody? If the universe is old and vast, why haven't we seen aliens? The discovery of these early galaxies makes the paradox infinitely worse. If massive, stable galaxies existed 500 million years after the Big Bang, then planets could have formed 13 billion years ago. Life could have started 13 billion years ago. There could be civilizations that rose, conquered galaxies, and died out before our sun was even a cloud of gas. We might be the latecomers to the party, walking into a venue that has been empty for eons, stepping over the dust of gods. If life is possible that early, the silence of the sky is deafening. It suggests that the Great Filter, the thing that kills civilizations, is incredibly efficient, or that the early universe was a graveyard of empires we will never know. Consider the Kardashev scale in the context of the early universe. A Type 3 civilization controls the energy of an entire galaxy. If galaxies formed this quickly, Type 3 civilizations could have emerged by redshift 5 or 6. They would have had billions of years to engineer the cosmos. Some astronomers have even jokingly, or nervously, suggested that some of the anomalies we see, like the impossible synchronization of galaxy rotations or the unexplained voids, could be the result of mega-engineering. While this is pure speculation, the fact that the timeline now allows for it is unsettling. We used to think there wasn't enough time for such things. Now the timeline has opened up a chasm of possibility. We are no longer protected by the "we are the first" assumption. We might be the bacteria growing in the petri dish of a long-dead experiment. We must address the cosmological constant problem, often called the worst prediction in the history of physics. Quantum field theory predicts that the vacuum of space should have an energy density $10 carat, $120 times higher than what we observe. We usually ignore this discrepancy because we can't solve it. But these early galaxies might be a clue. If vacuum energy was different in the past, if the constant isn't constant, it could explain how these structures formed against the flow of expansion. Perhaps the vacuum energy decayed from a higher state to a lower state, dumping energy into matter creation. This is linked to the concept of false vacuum decay, a scenario where the universe could suddenly drop to a lower energy state, incinerating everything at the speed of light. If early galaxy formation involved shifts in vacuum energy, it means the stability of our universe is precarious. We are walking on thin ice over a deep ocean of energy. The seed problem is another headache. To make a supermassive black hole or a galaxy, you need a seed, a clump of matter to start the process. There are light seeds, remnants of the first stars, roughly 100 solar masses, and heavy seeds, direct collapse gas clouds, roughly 100,000 solar masses. The standard model prefers light seeds because they are easier to make. But light seeds grow too slowly to create the monsters Webb is seeing. We are forced to accept heavy seeds, but making a heavy seed requires fine-tuned conditions. Gas that never cools, never fragments, and collapses all at once. These conditions should be rare, extremely rare, yet the universe is littering them everywhere. It implies that the early universe had a mechanism for mass production of heavy seeds that we do not understand. It was a factory for black holes. Let's look at quasar J03131806. This is the most distant quasar known, powered by a supermassive black hole 1.6 billion times the mass of the Sun, existing just 670 million years after the Big Bang. To get that fat, that fast, it would have to eat matter at the maximum theoretical limit every single second of its life since the moment of creation. It is a glutton that defies the laws of physics. It implies that black holes might have formed before the galaxies themselves. This flips the script. We usually think, gas to stars to galaxy to black hole in the middle. What if it was, black hole to gas falls into galaxy forms around it? This black hole first scenario changes the role of black holes from destroyers to creators. They would be the anchors of reality, the dark spikes that pin the galaxies to the fabric of space-time. The rotation of these galaxies is also a mystery. In the early universe, things should be turbulent, chaotic, and messy. Dispersion-dominated is the technical term, but some of these high-redshift galaxies appear to be rotation-dominated. They are spinning disks, organized, calm. A disk is a fragile thing. It is easily destroyed by mergers and collisions. Finding a calm, rotating disk in the violent mosh pit of the early universe is like finding a house of cards standing in the middle of a hurricane. It suggests that these galaxies had a shield, or that the environment was strangely orderly. Or, perhaps, the dark matter halos provided a protective cradle that dampened the chaos. It adds to the uncanny valley feeling. These objects are too perfect for their violent environment. We also have to talk about MOND again, modified Newtonian dynamics. This theory tries to eliminate dark matter by changing the laws of gravity at low accelerations. MOND has always struggled to explain the cosmic microwave background. But MOND loves these early galaxies. In MOND, structure forms much faster because gravity is stronger, without the need for the slow accumulation of dark matter. The success of MOND in predicting this specific anomaly is making some physicists uncomfortable. It's like the crazy person in the room suddenly getting the winning lottery numbers. If MOND is right, then dark matter, the thing we have spent billions searching for in underground detectors, is a fiction. It would mean we have misunderstood Newton and Einstein for a century. It is a radical, dangerous idea, but it is currently the only one smiling. Let's widen the lens to the Hubble tension again. We have the early universe measurement, 67 kilometers per second MPC, and the late universe measurement, 73 kilometers per second MPC. They don't match. The discovery of these galaxies adds a third point of tension, the growth tension. The rate at which structure grows, measured by a number called sigma 8, is also showing cracks. The universe seems to be growing structures slightly differently than the CMB predicts. We are seeing a pattern of failure. It's not just one number that is off, it's all of them, in systematic ways. The dashboard of the universe is flashing red warning lights. We can tape over one light, but when the whole dashboard lights up, you have to stop the car. We need to pull over and check the engine of the cosmos. Sociologically, science advances one funeral at a time, according to Max Planck. Old scientists cling to old theories, but the James Webb telescope doesn't care about tenure or reputations. It is a machine. It produces raw data. The crisis in cosmology is forcing a generational shift. Young PhD students are looking at this data and realizing the field is wide open. The standard model is no longer a fortress, it is a ruin. This is terrifying for the establishment, but exhilarating for the pioneers. We're entering a new Wild West of astrophysics where the maps are blank and the sheriffs, the laws of physics, are being questioned. It is a time of chaos, and chaos is where the truth usually hides. Let's acknowledge the role of artificial intelligence in this. The sheer volume of data from Webb is too much for human eyes. We use AI algorithms like Morpheus to classify galaxies pixel by pixel. These AIs are trained on simulations, but if the simulations are wrong, the AI might be hallucinating, or conversely, it might be finding things we told it didn't exist. In the case of these early galaxies, the AI flagged them as high probability, high redshift candidates. The machine saw the pattern before we did. We are relying on non-human intelligence to map the non-human cosmos. There is a strange synergy there. Synthetic minds exploring the synthetic-looking perfection of the early universe. Is it possible we live in a local void? The KBC void is a theory that the Milky Way exists inside a massive bubble of underdensity, about 2 billion light-years across. If we are inside a void, matter is flowing away from us towards the denser regions outside. This would skew our measurements of the expansion rate. It would make the local universe look like it's expanding faster than it really is. This could solve the Hubble tension. But does it explain the early galaxies? Not directly. In fact, if we are in a void, the universe outside is even denser than we think. This makes the baryon budget problem even worse. If the average density of the universe is higher, then the existence of these monster galaxies is slightly less impossible, but still catastrophic for our models of time. We must consider the dipole repeller. We know we are moving towards the great attractor, but we are also being pushed away from a void called the dipole repeller. The dynamics of our local universe are dominated by these invisible push and pull forces. Now apply this to the early universe. Were there primordial attractors and primordial repellers? If the early density field was extreme, the flows of matter would have been supersonic. Galaxies would have formed in the crash zones of these titanic rivers of hydrogen. We simulate the universe as a gentle fluid, but it might have been a raging whitewater rapid. The calm spirals we see today are just the foam left on the surface after the storm. There is a feature in the cosmic microwave background called the axis of evil. It is an alignment of hot and cold spots that shouldn't exist. It suggests the universe has a direction, an up and down. This violates the Copernican principle, which states the universe is the same in all directions, isotropic. If the axis of evil is real and these early galaxies are aligned with it, which some data hints at, then the universe is not a sphere. It might be a flattened ellipsoid or a rotating torus. If the universe has a shape, then the Big Bang happened differently in different directions. Time might flow at different rates depending on where you look. It breaks the symmetry of existence. This leads to the Bianchi models, mathematical descriptions of anisotropic universes. Some of these models allow for a universe that rotates. Kurt Gödel, Einstein's friend, found a solution to general relativity where the universe rotates. In a rotating universe, closed time-like curves are possible. That's fancy talk for time travel. If the universe rotates, you can theoretically travel into your own past. While we don't think our universe is rotating that fast, any deviation from perfect symmetry opens the door to exotic physics. The existence of these massive early galaxies forces us to look at these exotic models again. Maybe the rotation provided the centrifugal force that held these galaxies together or pushed them apart. Let's name names. GNZ11. For years, this was the record holder, a galaxy at redshift 11. We thought it was an outlier, a freak. Now we have JADE's GSZ130 at redshift 13.2. The numbers keep climbing. We are pushing back the curtain to just 330 million years after the bang. The gap between the beginning and the first galaxy is shrinking. Soon, they might overlap. If we find a galaxy at Z equals 20, we are in big trouble. Z equals 20 is the era of the first stars. If a galaxy exists there, it means the galaxy formed simultaneously with the first stars. That is physically impossible in a bottom-up universe. It would mean the universe was born with galaxies already inside it. The distance to these objects is mind-bending. JADE's GSZ130 is not 13.6 billion light-years away. That is the light travel time. Because the universe has expanded while the light was traveling, the galaxy is actually about 33 billion light-years away from us right now. This is the co-moving distance. The universe is bigger than the age of the universe multiplied by the speed of light. It creates a horizon problem. How did parts of the universe on opposite sides of the sky coordinate their temperatures if they were never in contact? Inflation solves this. But does inflation explain the clumpiness required for these galaxies? Some physicists argue that these galaxies are the first cracks in the theory of inflation itself. If inflation was not smooth, if it was bumpy, it would explain the monsters. Bouncing cosmology is the rival to inflation. It suggests the Big Bang was actually a big bounce, the result of a previous universe collapsing and rebounding. In a bounce scenario, it is possible that some structures, or at least the seeds of structures, survived the bounce. Imagine a universe that remembers its past life. If these galaxies are seeds from a previous eon that survived the crunch, it would explain why they are so big so early. They had a head start. They are the refugees from a dead universe, reborn in ours. It's a poetic, haunting thought. We are living in a recycled cosmos, and the anomalies are the debris of the previous iteration. Let's get back to the human eye. If you could stand on a planet in the early universe, the sky would be terrifying. The intergalactic medium was not yet fully ionized. It was foggy. You would see the massive blazing disk of your home galaxy, but beyond that, darkness, a wall of neutral hydrogen. You would be imprisoned in light, surrounded by a fog of dark. It would feel claustrophobic. The transparency of space we enjoy today is a luxury of the modern epoch. Back then, space was a thick, opaque soup. The fact that we can see these galaxies at all means they punched holes in that soup with the sheer violence of their radiation. They were the universe's first breathers, gasping for light in a suffocating dark. We often talk about the bullet cluster as proof of dark matter. It shows gas separating from mass during a collision. But the bullet cluster is a single event. These early galaxies are a population. They challenge the simulations that were tuned to fit the bullet cluster. We are seeing a, quote, tug of war between different epochs of evidence. The local universe says dark matter is cold. The early universe says dark matter is something else. Maybe dark matter evolves, maybe it decays. If dark matter is unstable and decays into radiation over billions of years, there would have been more of it in the past. Stronger gravity in the past would explain the rapid growth. We might be living in the era of diluted dark matter, the leftover dregs of a potent primordial substance. The crisis is not just academic. It affects our search for fundamental physics. If we can't explain a galaxy, how can we explain the quantum gravity that governs the singularity? We are trying to unite gravity and quantum mechanics, the theory of everything. But if our astrophysical data is wrong, our constraints for that theory are wrong. We might be trying to solve a puzzle with pieces from two different boxes. These galaxies are telling us that the box we are using, the box of general relativity plus lambda CDM, might be missing the corner pieces. And without the corner pieces, you can't build the frame. Consider the JWST deep field images again. Every dot is a galaxy, thousands of them. The deeper we look, the more we find. There is no edge yet. We haven't found the wall. We haven't found the moment where the lights go out. We expected to see a turnover, a point where galaxies become rare and then vanish. We haven't seen it. The universe is relentless. It keeps producing structure as far back as we can see. This lack of a turnover is the nightmare. It implies that if we built a bigger telescope, we would just see more. Is it turtles all the way down? Is the universe infinitely old? The data is taunting us with infinity. Population 3 stars, the first stars, were supposed to be the simple ancestors. But if the first galaxies were complex, maybe the first stars were complex too? Maybe the universe created heavy elements in the Big Bang itself. Standard Big Bang nucleosynthesis says no, only hydrogen, helium, lithium. But if we find carbon at Z equals 1,5, we have to break the Big Bang. Breaking nucleosynthesis is a big deal. It's the most robust prediction we have. If that is wrong, then our understanding of nuclear physics in the early universe is wrong. The dominoes keep falling. Let's visualize the merger tree again. In the computer, it looks like a root system, branching out. But the real data looks like a forest of trunks with no roots. The galaxies appear trunk first. They are thick and heavy from the start. Where are the roots? Where are the small, messy clumps? They must be there, but they are seemingly overshadowed by the giants. Or the giants consume the roots instantly. The cannibalism rate in the early universe might have been 100%. A universe that eats its own children to build giants. A Darwinian nightmare where only the massive survive the first epoch. The UV luminosity function is the technical term for how many bright things are there. The graph shows a line that should drop off. Instead, the line stays flat or even goes up at the high end. This excess of bright objects is what we are trying to explain. Is it because star formation is efficient? Or is it because the initial mass function, IMF, is top-heavy? A top-heavy IMF means that for every 100 stars born, 90 of them are massive giants, instead of the usual 1 or 2. If the early universe was a factory for giants, it would explain the brightness. But it also means the early universe was a place of constant supernovae, a sky flashing like a strobe light. The dust temperature is another clue. Dust glows in the infrared. If these galaxies are dusty, the dust must be hot. Hot dust implies active star birth, but we also see evidence of cold dust. Cold dust means the galaxy has had time to settle. Finding cold dust in the early universe is like finding an ice cube in a furnace. It shouldn't last. It implies that these galaxies have shielded interiors, deep, dark molecular clouds where the radiation of the young universe can't reach. Safe havens in hell. We must return to the observer bias. Are we only seeing the monsters because they are the only things bright enough to see? Yes. This is the Malmquist bias. But even accounting for bias, there are too many monsters. If you go fishing and catch a 100-pound tuna in a pond, you can say, I only caught it because it's big. But the existence of a 100-pound tuna in a pond is the problem, not your fishing rod. The pond shouldn't support the tuna. The volume of the early universe shouldn't support these galaxies. The dark side of this discovery is what it says about our future. If the universe changes its rules, If the laws of physics evolve, then we cannot predict the end. We talk about the heat death, where everything freezes. But if vacuum energy is dynamic, maybe the universe will rip apart, the big rip, or crunch back down. The big crunch. The stability of the laws of physics is our only comfort. These galaxies suggest that stability is an illusion. The laws changed in the past. They can change in the future. We are riding a beast we do not control. Let's imagine the civilizations again. If a species arose on a planet around a star in galaxy ZFUDS 7329 12 billion years ago, they would look up and see a universe that is denser, hotter, and smaller. They would see the cosmic microwave background not as invisible microwaves, but as visible heat. The sky would glow. They would be closer to the Big Bang than we are to the dinosaurs. Their cosmology would be totally different. They wouldn't need a telescope to see the curvature of space. To them, the expansion would be obvious. We are the blind ones, looking at the faded traces. They lived in the vivid reality. The clumpiness of the universe is measured by a parameter called SIGMA8. The tension here is real. Weak lensing surveys, looking at how gravity bends light today, say the universe is smooth. The CMB says it's smooth, but the existence of these galaxies says it was clumpy. How do you go from clumpy, early, to smooth, late? Entropy usually works the other way. Things get messier. Here, things seem to have smoothed out. Did the universe relax? Did the dark energy push the clumps apart? It's a reverse entropy problem. The arrow of time seems confused here. Primordial non-Gaussianity. It's a mouthful, but it's the leading suspect. It means the initial quantum fluctuations were skewed. Instead of a bell curve, there were spikes. These spikes became the seeds for the monster galaxies. If this is true, it gives us a window into the physics of inflation itself. It means the field that drove inflation, the inflaton field, was interacting with something else, a hidden field, a shadow sector. We are seeing the shadow of a second field that touched ours at the beginning of time, leaving these massive bruises on the sky. We are also looking at spectroscopic redshifts versus photometric redshifts. Photometry is a guess. Spectroscopy is the truth. Webb has now provided the spectroscopy. The guesses were mostly right. The confirmation bias argument is dying. We really are seeing what we think we are seeing. The denial phase is ending. The acceptance phase is beginning. And acceptance means rewriting the textbooks. The Chapter 1 of Introduction to Cosmology is now blank. We have to write it again. Think about the sheer scale. A galaxy is a collection of 100 billion suns. To assemble that, you need to move $10 carat, $42 kilograms of matter, across millions of light years. It is a logistical nightmare. Gravity is the only truck driver available, and gravity is slow. Unless the matter was already there? What if the matter was created in clumps? Primordial isocurvature fluctuations. Instead of the density changing, the type of matter changed. Pockets of pure baryons. Pockets of pure dark matter. If the universe was born curdled instead of smooth, the chunks would become galaxies instantly. It's the cottage cheese universe theory. Not elegant, but it fits the data. The monsters have names like the Sparkler, the Red Nugget, the Little Red Dot. Cute names for terrifying objects. The Sparkler is surrounded by globular clusters, balls of ancient stars. Globular clusters are usually old. Finding them around a young galaxy means the clusters formed even earlier. It pushes the timeline back to z=20 or z=30 again. The recursive nature of the problem is maddening. Every time we explain an object, we find parts of it that are even older. It's an infinite regress of age. We are approaching the Dark Age's limit. Neutral hydrogen absorbs light. This is the Gunn-Peterson trough. We shouldn't be able to see anything beyond z=10 or so because of this fog. But we are seeing things. This means these galaxies are blasting holes in the fog. They are reionizing their bubbles. They are localized lighthouses. But to be visible through the fog, they must be incredibly bright. Brighter than any galaxy today. They are hyperluminous. They are burning their fuel at a suicidal rate. They are the rock stars of the cosmos, burning out rather than fading away. The implication for us is existential. We exist because the Milky Way is a polite, well-behaved galaxy. It formed slowly. It didn't use up all its gas in the first billion years. It saved some for us, 13 billion years later. These early monsters used up everything. They are dead now. They are red and dead ellipticals. They had their party at the dawn of time and left nothing for the future. We are the scavengers living on the leftovers of the Big Bang. We should be grateful for the inefficiency of our galaxy. Inefficiency is why we are alive. The James Webb itself is a character in this story. It sits at L2, a point of gravitational balance, with its back to the sun. It is the coldest thing in the solar system, arguably. It is a time machine made of beryllium and gold. It is the peak of human engineering, staring at the peak of cosmic engineering. There is a poetic symmetry. We built a mirror to see the beginning, and the mirror showed us that we don't understand the beginning. The machine worked perfectly. It was our theories that malfunctioned. Simulation theory usually gets a laugh, but when you see glitches like this, objects that violate the rules of the engine, it stops being funny. In video games, if you load a level and the buildings appear before the terrain, it's a bug. These galaxies are buildings appearing before the terrain. The cosmic web was finished. Are we seeing a rendering error? Is the speed of light just the clock speed of the processor? It's a metaphor, but metaphors are all we have when the math breaks down. Let's look at the halo mass function. This predicts how many dark matter halos of a certain size should exist. The extreme tail of this function, the high mass end, is very sensitive to cosmology. Finding these galaxies means the tail is fatter than we thought. There are more rare events than a Gaussian distribution allows. It means the universe is heavy-tailed. Disasters, monsters, and miracles are more common than statistics predict. We live in a universe prone to extremes. The panic is subsiding into resolve. The astronomers are now in the bargaining phase of grief. Maybe if we tweak the star formation efficiency? Maybe if we change the initial mass function? They are trying to patch the hull of the ship. But the hole is too big. You can't patch a hole the size of a galaxy. We need a new ship. A new model. Maybe self-interacting dark matter? If dark matter interacts with itself, it can pile up faster. It's a new variable. Science loves new variables. What if the redshift is not just expansion, gravitational redshift? Light climbing out of a deep gravity well loses energy. These galaxies are massive. Maybe some of their redshift is because they are so dense? It's a long shot. But we are checking everything. The tired light idea keeps lurking in the background, like a ghost. We exorcised it in the 20th century, but it haunts the 21st. The cosmic variance safety net is gone. We have surveyed multiple fields, CEERS, glass, NG deep. The monsters are everywhere. They are not a fluke. They are a feature. The universe has a monster feature. It likes to build big things early. It's a precocious universe. It didn't crawl. It walked. It didn't walk. It ran. And we are just now realizing how fast it was moving. Occam's razor says the simplest explanation is usually right. The simplest explanation here is that our timeline is wrong. The complicated explanation is that star formation efficiency was 100%, the IMF was top-heavy, dust is weird, and dark matter is self-interacting. That's a lot of assumptions to save a theory. Maybe the simple answer is, the Big Bang happened earlier, or differently, or not at all. The razor is cutting deep. We are left with the mystery, and mystery is good. If we knew everything, science would be dead. This discovery has revitalized cosmology. It has given us a new dragon to slay. The impossible galaxies are the dragons on the edge of the map. Here be monsters. We are sailing towards them. We might fall off the edge of the Earth, or the edge of known physics, but we have to look. As we close this chapter of the investigation, remember this. The light from these galaxies has been traveling for 13 billion years to hit the gold mirrors of Webb. It brings a message. The message is, you are wrong. It is a humbling message. The universe is not what we thought. It is bigger, older, and stranger. And that is why we look up. Not to be confirmed, but to be surprised. We are halfway through our journey into the dark. The next phase involves the theories of everything: string theory, loop, quantum gravity, the multiverse. Can they save us? Or will they only deepen the mystery? The impossible galaxies are just the door. We are about to walk through it. We are standing at the precipice of what philosophers call the end of certainty. For a century, we believed we had the story of the universe roughly correct. We thought it was a linear narrative: Big Bang, cooling, dark ages, stars, galaxies, us. But the massive galaxies at redshift 10 have taken a sledgehammer to that timeline. This is not just a scientific problem, it is a psychological one. We crave order. We crave a beginning, a middle, and an end. The data is suggesting that the beginning was far more chaotic and developed than we assumed. It suggests that the universe didn't start as a blank canvas, but as a painting already in progress. This leads to the chilling in situ formation theory, the idea that galaxies didn't slowly assemble from small pieces, but collapsed in place from vast pre-existing overdensities. If this is true, the blueprint for the Milky Way was etched into the cosmos within the first second of time. We were fated to exist, chemically and gravitationally, from the very start. To explain this in situ collapse, we have to look at the Higgs field. The Higgs is what gives particles mass. In the early universe, the Higgs field might have been in a different state, or it might have fluctuated wildly during inflation. If the Higgs field had bumps, particles in certain regions would have gained mass earlier or differently than in others. These heavy regions would become the anchors for the impossible galaxies. We are effectively looking at a fossil record of the Higgs field itself. This connects the smallest thing we know, the boson, to the largest thing we know, the galaxy. It implies that the impossible galaxies are actually quantum mechanical artifacts magnified to the size of the cosmos. We are living inside a quantum fluctuation that got out of hand. The monstrosity of these galaxies is just the visible expression of a subatomic roll of the dice that happened 13.8 billion years ago. This brings us to string theory. String theory posits that there are extra dimensions curled up at every point in space. These dimensions determine the laws of physics. In the landscape of string theory, there are $10 carat, $500 possible vacuums. Most physicists hate this number because it makes prediction impossible. But the impossible galaxies might be evidence that we live in a very specific, very rare valley of this landscape. A valley where gravity is just strong enough to build monsters, but not strong enough to crush them into black holes immediately. If the early universe explored different parts of this landscape, if the laws of physics evolved as the universe cooled, then the high redshift universe might have operated under different rules of string tension. We might be looking at a time when the extra dimensions were shifting, settling into their current shape. The galaxies are the scars left by the settling of dimensions. We must also consider entropy. The second law of thermodynamics says entropy, disorder, always increases. The early universe was supposed to be low entropy, smooth, ordered, uniform. But a universe filled with massive, clumpy galaxies is a high entropy state compared to a smooth gas. This creates an entropy problem. How did the universe get so messy, so fast? Unless it started messy. Roger Penrose proposed conformal cyclic cosmology, CCC, where the end of one universe becomes the Big Bang of the next. In CCC, the mess of the previous universe, its black holes, leaves Hawking points on the sky of the new universe. Could these massive galaxies be the Hawking points? The gravitational ghosts of supermassive black holes from a universe that died before ours was born? It's a terrifying thought. We are building our homes on the gravestones of a previous reality. The wall of the Big Bang is usually depicted as a fire, but what if it was a phased transition, like water freezing into ice? When water freezes, it creates crystals, cracks, and bubbles. It is not a smooth process. These topological defects, cosmic strings, domain walls, monopoles, are theoretical scars in spacetime caused by the cooling of the universe. We haven't seen them, or have we? Some theorists argue that cosmic strings, infinitely thin, super-dense cracks in the universe, could have acted as the seeds for these galaxies. A loop of cosmic string would have immense gravity, pulling gas in instantly. If these galaxies are seeded by cosmic strings, it means the fabric of space is cracked, and the galaxies are the scabs forming over the wounds. We are living in a broken universe that is trying to heal itself with gravity. Let's zoom in on the gas reservoirs. For a galaxy to form stars this fast, it needs a constant supply of cold hydrogen. It needs a pipeline. We call these cold accretion flows. Computer simulations show narrow filaments of cold gas piercing the hot halo of a galaxy, feeding the center like an umbilical cord. But to sustain the growth of the impossible galaxies, these pipelines would have to be fire hoses. The flow rate would be supersonic. The gas would be crashing into the galaxy core with the energy of 1 billion nuclear bombs every second. The turbulence in these early disks must have been unimaginable. Yet, as we noted, some look calm. This is the disk paradox. How do you feed a beast a supersonic meal without making it choke? The fluid dynamics of the early universe seem to have a laminar flow quality that we cannot replicate in our simulations. Nature is a better engineer than we are. There is a psychological element to denial. When the first high redshift candidates appeared, the community said, they are just dusty, low redshift galaxies. Then spectroscopy ruled that out. Then they said, the masses are overestimated. Then we confirmed the stellar mass. Now they say, maybe the initial mass function is weird. We are running out of places to hide. The scientific method is designed to kill false theories, but it hurts when the theory being killed is the one you grew up with. We are watching the stages of grief play out in peer-reviewed journals. The acceptance stage will come when we finally admit that the universe is capable of hypergrowth. Once we accept that, the fear goes away, replaced by the awe of a universe that is far more potent and creative than our conservative models allowed. The 21 centimeters hydrogen line is our next great hope. This is a specific radial wavelength emitted by neutral hydrogen. We are building giant arrays like the SKA, Square Kilometer Array, to map this fog. When we turn these machines on, we will see the dark ages directly. We won't just see the galaxies, we will see the spaces between them. If the impossible galaxies are real, the 21 centimeters map will look like Swiss cheese. Huge holes punched in the hydrogen fog very early on. If we see these holes, it is the final confirmation. It will be the picture of the crime scene taken with a different camera. It will show us exactly how the monsters ate the fog. The 21 centimeters line is the black box recording of the universe, and we are about to listen to the tape. What if the fine structure constant alpha was different in the past? Alpha determines the strength of the electromagnetic force. If alpha was slightly larger, atoms would be smaller, energy levels would shift, and star formation might be easier. A changing alpha is a heresy in physics. Constants are supposed to be constant. But measurements from distant quasars have just hinted, that alpha might vary across the sky. If the laws of physics are local rather than universal, then these galaxies formed in a high alpha patch of the universe. It essentially means we live in a patchwork universe, where the rules of the game change depending on which room you are in. We are in the slow room. They were in the fast room. Let's revisit the Great Filter. If life requires heavy elements, and these galaxies created heavy elements 500 million years after the Big Bang, then the window for life opened 13 billion years ago. The universe has been habitable for 95% of its history. We have only been here for the last 0.002%. If intelligence is inevitable, where are the others? The silence suggests that intelligence is not inevitable, or that it destroys itself with 100% certainty. Maybe these early galaxies were the cradles of the first civilizations, and they burned themselves out? Maybe the red and dead galaxies are dead, not because they ran out of gas, but because they were weaponized? It is a dark sci-fi thought, but in the absence of data, the mind wanders to the dark. The JWST is just the beginning. We are planning the Habitable Worlds Observatory and the next generation VLA. But we are realizing that we might need a different kind of telescope. We need a gravitational wave observatory in space. The LISA mission, Laser Interferometer Space Antenna, will detect the mergers of supermassive black holes. If the early universe was filled with these monsters merging, the background hum of gravitational waves will be deafening. We might not be able to see the Big Bang with light, but we might be able to hear the crashing of these early giants. The universe is noisy. We just haven't put our ear to the ground yet. When LISA launches, we might hear the screams of the early universe. Dark energy is usually thought of as a late-time phenomenon, something that only started dominating recently. But if early dark energy existed, it would have essentially pre-stretched the universe. This would change the acoustic scale, the size of the sound waves from the Big Bang. This would make the universe look younger than it is. If we correct for this, the impossible galaxies fit. But it requires us to believe in a substance, early dark energy, that appeared, did its work, and then vanished without a trace. It is a ghost in the machine, a convenient ad hoc fix. But sometimes, ghosts are real. In quantum field theory, fields can appear and disappear through phase transitions. The universe might be more transient than we like. The super-Eddington accretion is a key concept. The Eddington limit is the speed limit for feeding a black hole. If you feed it too fast, the radiation blows the food away. To explain the quasars at z equals 7, we need them to eat at 100 times the Eddington limit. How? Maybe the magnetic fields trapped the gas? Or maybe the black holes were hiding in a cocoon of dust that absorbed the radiation? If they broke the Eddington limit, they broke the traffic laws of the cosmos. It implies a chaotic, lawless era where the regulators, feedback loops, were offline. It was the Wild West of gravity. We are also looking at globular clusters. These are balls of 1 million stars that orbit our galaxy. They are ancient. Some of them seem to be almost as old as the universe. The impossible galaxies might be the factories that made these clusters. We might be seeing the birth of the globular clusters that now orbit the Milky Way. It connects the local to the distant. When you look at M13 or Omega Centauri through a backyard telescope, you are looking at the survivors of this violent epoch. They are the refugees that made it to the modern era. They are the time capsules carrying the chemical memory of the monster galaxies. Cosmic dawn is a misleading term because it implies a slow sunrise. The data suggest a cosmic switch. One moment, dark. The next, blazing light. The reionization process was likely patchy and explosive. The bubbles of ionization grew and merged. We are trying to map these bubbles. If the bubbles grew too fast, they would have heated the gas and shut off star formation in small galaxies. This is the dwarf galaxy problem. Where are all the small galaxies? Maybe the monsters killed them? The radiation from the giants might have sterilized the dwarves, preventing them from ever forming stars. The giants ate the lunch of the little guys. Let's talk about dust production again. It takes a supernova to make dust, but it takes millions of years for a star to go supernova. If we see dust at z equals 14, it means the first generation of stars lived and died in a blink. These stars must have been 100 or 200 solar masses. Pair instability supernovae. These are explosions so violent they leave nothing behind. No black hole, no neutron star, just pure mist. If the early universe was dominated by pair instability supernovae, it was a fireworks display of total annihilation. It enriched the universe with oxygen and silicon instantly. We are made of that ash. The iron in your blood might have come from a star that died 13.5 billion years ago in one of these impossible galaxies. The information paradox of black holes is usually about quantum information. But there is a cosmological information paradox. The universe contains more complexity, information in these galaxies, than the initial conditions should allow. Where did the extra information come from? Did it leak in from the multiverse? Or did it emerge from quantum entanglement? Some theories suggest space-time itself is stitched together by entanglement. If the entanglement entropy was higher in the past, the universe could support more structure. It's deep theoretical physics, but it's the only place left to look for answers. The it from bit concept, that the universe is made of information, might be key. We are finding too many bits in the early file. Panic is a strong word, but let's use disorientation. We are disoriented in time. We don't know how old the ground beneath our feet really is. The Earth is 4.5 billion years old. That date is solid, radiometric dating. But the universe's age is derived from a model. If the model changes, the age changes. What if the universe is 100 billion years old? Then the Earth is a very recent arrival. What if the universe is infinite? Then we are nothing. The impossible galaxies are forcing us to confront the scale of time in a way we haven't since Hubble discovered the expansion. We are feeling the vertigo of the infinite. We need to discuss the scientific method as a survival strategy. We survive by building models that predict the future. If our model of the past is wrong, our predictions for the future are suspect. The Big Rip, Big Freeze, Big Crunch, these are all based on lambda CDM. If lambda CDM is wrong, we don't know how the universe ends. Maybe it doesn't end, maybe it cycles. The cyclic universe models, ekpyrotic universe, suggest colliding brains, higher dimensional sheets, cause big bangs periodically. If we are in a cyclic universe, these old galaxies might be the debris that didn't get wiped clean by the last bang, a stain on the new canvas. The voids between galaxies are expanding. This pushes galaxies apart. But inside the impossible galaxies, gravity won. It defeated the expansion. This victory was decisive and early. It proves that gravity is not just a weak force. It is a patient and relentless one. The clustered nature of these galaxies suggests that they formed in the nodes of the cosmic web. We are mapping the skeleton of the universe. The bones are thicker than we thought. The universe has a heavy skeleton. It is not a fragile thing. It is built to last. Dark matter is still just a placeholder name. We don't know what it is. WIMPs? Weakly interacting massive particles? Axions? Sterile neutrinos? The impossible galaxies might force us to choose. WIMPs move slowly, cold dark matter. Axions can form waves, fuzzy dark matter. Sterile neutrinos are warm, warm dark matter. Warm dark matter washes out small structures. It makes it harder to form galaxies. So the impossible galaxies effectively kill the warm dark matter theory. They demand cold or fuzzy matter. We are narrowing down the suspects by seeing what couldn't have built the monster. The monster needs a specific kind of food, dark matter, to grow this big. The James Webb has a limited lifespan. It has fuel for 20 years. We have 20 years to solve this. It is a race. Every day, data comes down. Every day, a graduate student finds a new anomaly. The pace of discovery is frantic. We are in a golden age of cosmology, but it feels like a golden age of confusion. We are drowning in data but starving for understanding. This is better than the alternative, no data, but it is exhausting. The human mind is trying to wrap itself around a reality that is fundamentally alien. Let's imagine the sky of the future. If the universe keeps expanding, eventually, all other galaxies will disappear over the horizon. We will be alone. But if the impossible galaxies imply a different expansion history, maybe the future is different? Maybe the expansion will stop? If the clustering is stronger than we thought, maybe gravity will win in the end? The Big Crunch might be back on the table. A universe that collapses back into a singularity. A universe that breathes in and out. Fire and ice. We are currently in the ice phase expansion, but the fire might return. The red nuggets. These are the massive, compact, dead galaxies at z=2 to z=4. They are the descendants of the impossible galaxies at z=10. We can trace the lineage. The monsters grew up, burned out, and became the dense cores of modern giant ellipticals. The center of M87, the galaxy with the famous black hole picture, contains the corpse of one of these ancient monsters. We have seen the bodies in the local universe. Now we are seeing them as babies. The connection is confirmed. The lineage is real. We are looking at the baby pictures of the biggest things in the universe. Morphology is the shape of galaxies. Spirals, ellipticals, irregulars. In the early universe, we expected irregulars, train wrecks. We found disks and spheroids. The shapes were already defined. This means the Hubble sequence, the tuning fork diagram of galaxy shapes, was in place at the dawn of time. Order is not an emergent property. It is a fundamental one. The universe knows how to make a spiral. It doesn't need trial and error. It nailed the design on the first try. This platonic perfection of early forms is unsettling. Turbulence. The Reynolds number of the early universe plasma was huge. It should have been a mess. But the cold disks suggest the turbulence dissipated quickly. How? Magnetic fields? If the early universe was highly magnetized, the magnetic fields could have smoothed out the turbulence, acting like a straitjacket for the gas. Primordial magnetic fields. Another hypothetical. But if they existed, they would explain the order. We might be living in a magnetic universe as much as a gravitational one. Spectroscopic confirmation of a galaxy at z equals 14 would be the mic drop. We are close. Jade's GSZ130 is at 13.2. The hunt for z equals 14, z equals 15 is on. It's a high-stakes game of limbo. How low in time can you go? The lower we go, the more impossible it gets. If we hit z equals 20, we hit the wall of the first stars. If we find a galaxy before the first stars, impossible by definition, then we are seeing something that isn't a galaxy. A dark matter clump that glows? A boson star? The vocabulary fails us at that edge. The cosmic variance argument is truly dead. We have to accept that the average universe is not what we thought. We have to re-normalize our expectations. The standard model is a map drawn by Europeans in the 15th century. Good for the local area, terrible for the New World. Webb is our Columbus. It just landed on a continent that isn't on the map. We are exploring the terra incognita of the first billion years, and it is inhabited. Peer review is slow. The papers take months. But the ArcSolve preprint server is fast. The debate is happening in real time. You can watch the scientists argue in the comments sections of physics blogs. It's a messy human process. But out of this mess, a new truth will emerge. We are watching the scientific method operate at the speed of the internet. The crisis is being crowdsourced. What does it mean for me? It means you are part of a universe that is more efficient, more creative, and more mysterious than you were told. You are not the result of a slow, accidental grind. You are the result of a rapid, explosive, determined process. The atoms in your body were forged in the fires of monsters. You are stardust, yes, but you are the stardust of impossible stars. That makes you a little bit impossible too. The future of this research. Webb is just the start. We will build bigger telescopes. But will they solve it? Or just find more mysteries? The history of astronomy suggests the latter. We solve one riddle, we find three more. The fractal nature of knowledge. The more we know, the more we realize we don't know. The boundary of our ignorance expands as our knowledge expands. We are growing our ignorance. And that is a beautiful thing. Dark energy might be a fluid. Quintessence. A scalar field that evolves. If dark energy is quintessence, it changes over time. This would explain everything. The expansion rate changes, the age changes, the structure growth changes. It's the master key. But we haven't found the particle for it. It remains a mathematical ghost. Until we find it, it's just numbers on a page. But the numbers are pointing to it. The great attractor pulls us. But what pulls the great attractor? The Shapley supercluster. And what pulls that? The universe is a web of flows. In the early universe, these flows were torrential. The impossible galaxies were the rocks in the stream, gathering debris. They grew because they were in the right place in the current. Location, location, location. Even in cosmology, it matters. Simulations are now running 24/7. Supercomputers like Frontier are trying to replicate the Webb data. They are tweaking parameters. Turn up the feedback, turn down the cooling, add more dark matter. They are trying to hack the universe in silicon. If they can reproduce the monsters, we win. If they can't, we need new physics. The computers are sweating. Biology analogy. Evolution has punctuated equilibrium, long periods of stasis, sudden bursts of change. Maybe the universe evolves like that? The Big Bang was a burst, then stasis, then reionization, a burst, then stasis. We are in a stasis period now. The early universe was the Cambrian explosion of astrophysics. Everything happened at once. The weird body plans, galaxies, were tested. The survivors kept going. Why us? Why are we here to see it? We live in the brief epoch where the universe is transparent and filled with stars. In the far future, the stars will die. In the far past, they hadn't formed. We are in the stelliferous era, the era of light. We are the witnesses. It is our duty to look. If we don't look, the universe is a play performed to an empty theater. We are the audience. The black hole information paradox suggests that information is never lost. If these early galaxies disappear into black holes, their information is preserved on the event horizon. The history of the early universe is written on the surface of black holes. We just need to learn how to read the braille of gravity. Lithium. The third element. It's the orphan. We can't explain it. The impossible galaxies might have burned it all, or created it. The lithium dip in old stars is a clue. It tells us the nuclear furnaces of the past were different. The fire burned differently back then. Isotropy. The universe looks the same in all directions. But does it? The hemispherical power asymmetry in the CMB says one side of the sky is stronger than the other. If the impossible galaxies are clustered on one side, it confirms the lopsided universe, a universe with a limp, a universe that is not perfect. The void. We fear the dark, but the dark is where the answers are. The voids between galaxies are not empty. They are full of dark energy. They are the laboratories of expansion. By studying the nothing, we understand the something. The impossible galaxies are the islands. The void is the ocean. We need to study the ocean too. Time dilation. We see the past in slow motion. But to the people in the past, time was normal. They lived their lives at normal speed. They didn't know they were ancient. They thought they were modern. We are the ancients of the future. Someone will look back at us and say, how did they exist in the primitive epoch of the Milky Way? It's all relative. The end. How does it end? If the universe is older, maybe it ends sooner. The Big Rip could happen in 20 billion years, or 100. The uncertainty is the thrill. We are walking on a wire, and we don't know how long the wire is. Complexity. The universe tends towards complexity before it dies. We are the peak of complexity, brains. The early galaxies were the peak of gravitational complexity. We are the echoes of their gravity. Translated into biology, we are the impossible galaxies made flesh. The great silence. The radio telescopes are listening. We hear static. But maybe the static is a signal we don't understand? The impossible galaxies were loud in radio. Maybe the signal is there, buried in the noise of the Big Bang? Dark flow. A controversial detection of galaxy clusters moving towards a point beyond the horizon. If real, it means our universe is being pulled by something outside the universe. A neighbor? The impossible galaxies might be riding this flow, drifting towards the exit. Beauty. We shouldn't forget the aesthetics. These images are beautiful. The cosmic cliffs of Carina, the pillars of creation. The impossible galaxies are red jewels on black velvet. Even if they break physics, they are stunning. Truth is beauty, even when the truth is terrifying. Paradigm shift. Thomas Kuhn coined the term. We are living in one. It happens once every 100 years. Copernicus, Newton, Einstein. Now, we don't have a name for the new guy yet. Maybe it's an AI? Maybe it's a team? The next Einstein is analyzing the Webb data right now. The human cost. Astronomers are tired. They are working double shifts. The data doesn't stop. It's a fire hose. They are heroes of the intellect, battling the entropy of ignorance. We should salute them. They are the cartographers of the impossible. The next question. If the universe is 26 billion years old, what happened in the first 13 billion? A lost history? A prehistory? We have to fill in the blank pages. The book of the universe just got twice as long. We are now 2/3 of the way through the script. The mystery has deepened, the science has broken, the philosophy has turned dark. But we keep going. Because the only way out is through, we have to go deeper into the dark to find the light.